Welcome to IT Pro TV. I'm your host, Don.
Vector live from San Francisco.
You're watching IT Pro TV.
Welcome to your CompTIA Security Plus series. I'm your show host, Cherokee Booth. We've actually made it to part 3. This is, of course, the 3rd episode where we're speaking about different types of attacks. And again, with us today, we have Mr. Wes Bryan. Thank you for joining us, Wes.
Hey, thanks for having me here. Yeah, we're working on a small mini-series here. Definitely a Stephen King novel if we don't wrap it up soon. Just kidding.
Unfortunately, there are a lot of different types of attacks
That's right, there are, and we have to talk about every one of them, and we certainly want you prepared for the exam. So we are back, that's right, with a part 3. And some of the things that we've talked about in the past episodes, we've talked about a lot, right? We've talked about things like denial of service attacks. We've talked about just all sorts of different types of attacks, cross-site scripting, cross-site forgery request type attacks, buffer overflow, so all kinds of good things. If those don't sound familiar to you, we also talked about in the first part social engineering and the principles of effectiveness for social engineering, if I could say that right. Go back and check those episodes out, the parts to this episode, if you will, and then come back and see us here, because we left off in the last episode. We were talking about domain hijacking, right? And the fact that that is a transference of a domain name from one registrar to another, but it's unauthorized. The process that it takes to undo that, to reverse that change, it can be so daunting that a lot of times these will go undisputed, unless if it's, you know, a domain name that is really making some people some money. I do have an instance where I mentioned a law firm, and that actually happened, where www.mla.com, I believe, I have it written down somewhere, it was a law associates, right? And it had been transferred illegally, unauthorized, to somebody else, and it cost this man a lot of money. In fact, so much so that he didn't think that he was going to get the domain name back. That was a few years ago. Happy to say that that domain name has been returned to its original owner, but it cost him like $250,000. So we're not talking about chump change here. We're talking about the legalities and the process to reverse that can be very, very complicated. Now, the next thing, kind of along that lines of where domain names start to come into play for us, and people kind of play on, well, Wes's ability to type, is hijacks and related hijacking attacks. The first two that I want to take care of are what are known as typo squatting. It's a form of URL hijacking in which it basically relies on anybody who's using the internet's ability to type, right? Typos. You want to go to Facebook, right? And instead of spelling it Facebook, you spell it FCE. book.com, right? And it takes you to another website, right? So that's what they do. You know, Google with too many zeros in it, right? Google with .net.
Transposing any letters.
Very good. Yeah, exactly. Putting a 3 in there, you know, throw a little leet in there. But the point being is that you are taken to a website that is not the one that you intended to go to based on some kind of typo, hence the term typo squatting. Now, Cherokee, we were kind of talking about this before we started.
Sure.
You have heard of an interesting URL type hijacking attack, right?
Yeah, so if I were to go ahead and register a domain with a registrar, like you had mentioned before, GoDaddy, a lot of these companies will give you a trial period before you actually commit and complete that registration process. So if an attacker is using this time to squat, per se, they haven't paid, they haven't fully complied with whatever authentication requirements that registrar has. So they can kind of get some free advertising out of the deal and redirect you to that great pharmaceutical website or whatever it is that they just kind of like hop around. They're squatting without paying, if you will. So
a perfect place to do that would be like on Black Friday here in the States, right, where there's a lot of people just there. They're grabbing onto their wallets and they're looking for the deals. Boy, if I can get some free advertisement out there and I got this deal that you just can't refuse, then I can probably make some money. And then in a couple of days, the site is no longer existent. So great example here. The other one that they call is clickjacking, and clickjacking is interesting because what that does, This is I call it dirty pool, right? What ends up happening is you have a link that says, hey, sign me out or continue shopping or something, and they put a link just near it, just under it. That's right. Where you go up and you click that button, and that wasn't the place that you intended to go. Or for here's another one that they'll do. They'll have an image, right? And the image you don't realize, you wouldn't think, oh, it's clickable, and you go up there and you click on it, and it takes you to a completely different location of the web page, or maybe even to a completely different website. That's clickjacking. Again, just hidden links that seem legit. They're clickable, and they redirect you, redirect the victim to some kind of unintended location. The other one that they call out is called session hijacking. This one is interesting because this relies on a man-in-the-middle attack. We had talked about the MITM attack, right? The man-in-the-middle attack
not
is being...
monkey in the middle.
That's right, not monkey in the middle, definitely not. So remember we have a source and destination of the communication, right? That's what we do in networks, right? I'm going to send communications to another endpoint. And then we have the hacker that stands in the middle, and they're eavesdropping on the communication, maybe capturing that data. In this place, what they're going to do is they're going to probably try to capture that information. All right. In fact, I got kind of a diagram here. So, for instance, we've got a web client, and it could be any of the web clients, guys. I'm not picking on any one in particular. That's why I've got a few of them here. I couldn't find Safari. They're all, this could happen. It's not really about the web browser. More sometimes it is about, like, for instance, stealing a session cookie. See, the session cookie, HTTP, it's stateless. It doesn't remember anything, right? It's kind of like me. It can't remember anything, can't remember yesterday. So what ends up happening is when you connect to a website, right, if you disconnect from that website and then you connect back to it, HTTP says, oh, good to see you for the first time. And then you disconnect and you connect again. TTP says, oh, good to see you for the first time, right? So we use things like cookies. Cookies contain session information that says, this is where you were on the web page, this is what your shopping cart looked like at the time, so that when I disconnect and I reconnect, you ever reconnected to a website and still been logged in? Maybe still had some of those transactions that you were doing that were pending? Well, imagine if I was a hacker here and I got in the middle, the attacker, right, in the man-in-the-middle attack, and I capture and I store that information, right? You have an authenticated session that keeps some of that information in that session cookie, and if I can get that session cookie, then essentially what I can do is I can turn around and I can replay it to the server. Now, it could be later. That would be a replay attack. Could be during the authenticated session. And now, according to the web server, it doesn't know. It sees the session cookie. I've got the cookie now as the attacker. It thinks that I am the victim. And essentially, we take the victim completely out of the communication, and they can perform whatever type of attack they want to from there, whether it happens to be a logged-in session with your banking information, maybe something like a website that you go do e-commerce, like Amazon.com or something like that, and now there's no real way for the server to tell that you, the attacker, are not the victim, right? There's just no way for them to tell. So that's a little bit about session hijacking. Now, a couple of the other things that they call out here, too, I want to talk about. Don't really have a diagram for this one. This one is a newer attack, right? And this is where the man-in-the-browser attack. See, the man-in-the-middle attack, see, we can see the communications, right? We can see what's going on as we eavesdrop on them, but the man in the browser is usually really isn't a person, right? It's not a human entity, if you will. It's a piece of code that attackers put into the browser, right, so that they can send it against the web server, and they can listen into information if they need to. So it's a little bit different. It doesn't necessarily mean that there's a human element actively in the session like a man-in-the-middle attack, more as it is a piece of code that's embedded into the browser. And again, hence the term man in the browser. 0 day. 0 day is an interesting concept. 0 day is really about new threats. All right. When we talk about 0 day, this is when your computer systems are at their most vulnerable state. This is when an exploit is found, and nobody knows about it. Nobody. Not your antivirus companies, right? Your security solutions. Nobody's aware of it. McAfee, Trend Microsystems, you know, Symantec, all the big guys, right? They're not even aware of that this has happened. All right, that's 0 day. It means it's the first time that this exploit has happened, and because nobody knows it even exists, nobody has a patch for it. Nobody has a fix for it. They say that sometimes it could take up to 8 months.
I know, it was ridiculous. I think Symantec came out with a ridiculous statistic that it's very misleading, the name. It can go unpatched for a very long time, or even undiscovered.
Yes, and undiscovered was up to 8 months. They said it could go to a year or even more than a year before it's actually patched.
Like 300 days before a solution was found. So.
Yes, and that's scary if you think about it, because the fact of the matter is, The sun doesn't set on the hackers, and a lot of times when it sets on the hackers, that's when they go to work, right? So it's a revolving door. Remember, security is not a destination to be reached, it's a journey to be traveled upon, right? So they're constantly coming out with new things. And because of that, that's why we need things like heuristics, we need sample submissions, but again, 0 day is just when an attack or an exploit has happened, nobody knows about it, and nobody has a solution for the problem. So you definitely have to worry. You can also think of just 0 day as being a brand new threat that nobody's aware of yet. Hacking conventions, right? That's why they have hacking conventions, right? You have companies that pay. Google, I don't know if they're still doing bug bounties, but are they doing bug bounties?
Increased them. Microsoft and a couple of the major companies have increased to ridiculous. So ridiculous payouts here, guys.
Yeah, definitely. And these bug bounties are to find out 0 day exploits, right? Much better to pay a white hat, if you will, or it could be a black hat, right? That's maybe got a conscience. But,
so gray.
Right, also gray. That finds that exploit and then lets the company know about it. And then the company implements a solution and lets the rest of the world know about it, right? It's one of the reasons that they have those. So we can find these exploits before somebody that doesn't have a conscience, the black hat, well, they have a conscience about making their wallets fatter and getting more money before they find it, and then they exploit it to whatever their malicious gain is, whatever their evil intent might be. All right, so I think that's got the hijacking and related attacks there. We do have to talk about something that I really don't have a slide for as well. That's called driver manipulation. Driver manipulation can happen for legal purposes, for known reasons. I'll give you an example. So one of the things that they call out is shimming, all right? We actually have these where they're legit, right? In Microsoft, right? And Cherokee, I know you're familiar with, very familiar with like Windows Server and the Windows clients, right? We have what's known as the Application Compatibility Toolkit, right? As you move from different versions of an operating system, there's a potential that the drivers that are in the operating system don't work when the new operating system is put into place, or an application for that matter, right? We're focused on drivers here, but applications too. So what do? You create a small fix called a shim. What happens is your normal process is in a driver context. Think about what a driver does, right? A driver takes that high-level programming language, translates it down into something, the low-level, like assembly, if you will, machine code that our hardware relies on to or react to. If I put a shim in the middle of it, right, it's a temporary fix that says, okay, well, now when the operating system, since it's not compatible, calls down, the shim basically formats it in a way that it can talk to the driver, and it's basically a compatibility fix. Now, one of the things I want you to keep in mind with driver manipulation, like unauthorized, right? This is when you put a hook, right? And what happens is when the operating system's supposed to be calling down to the driver, that shim intercepts it, right? And that's a lot of times what rootkits do. Rootkits intercept calls and they redirect them back up to the the user, and they can say whatever they want, right? So it works no different than the same way applications shimming works, right? And again, as an example of a legal shim, we have those inside of the ACT within Windows deployment tools. What else? Credit card shimming. You ever heard of that? Maybe you haven't. You've heard of the credit card skimmers, right?
Yeah.
Shimming's the same thing, right? It's just an interchangeable term. They call it shimming, right? Because what happens? You have the EMV, the standard for European and American credit cards, right? It's a little chip that sits on the card itself today. Well, that what happens is they put a little shim detector, a little device around what you put your card into, and it intercepts the communication between that chip and whatever the authenticating or device is that's inside of the ATM. It intercepts it, right? And it sends it somewhere else, and it sends it usually over a wireless communication to somebody that's waiting on the side of the van with the van. I don't know if they have a van or not, but waiting there to capture that information.
Has to be creepy.
Has to be creepy. It means it can't have windows either. That's essentially the way the credit card skimmers, they call them skimmers, but it's a shimming attack is what it's doing.
I've seen, Wes, online recently, a lot of gas stations will, even if they were having issues or it was a problematic location and they've had, these types of attacks happen there, they have these like stickers and it says if this sticker has been damaged in any way, please call and you'll have a 1-800 number. So those devices can't easily be added to particular ATMs, gas pumps, things like that.
Yeah, and one of the things that we could do with driver shimming in a malicious sense is to do, well, Windows, a lot of your operating systems already do this. It's just important to never bypass it, is to do driver signature enforcement, right? For instance, in Windows, you have 64-bit drivers. They have to be digitally signed. They have to be basically hit with a little bit of electronic signature there, a little electronic information that says, yeah, we know what this driver is. We know what it does. We've tested it. It's gone through a rigorous process, and Microsoft's got their seal of approval. In this case, I'm talking about Windows, right? So that when that driver executes, it's already trusted. We know what it is. And if there is a refactoring, right, a repurposing of the driver that we're not aware of, if there's a shimming that happens, we're going to be aware of it because the driver signature is going to catch it. So that's one of the things that you can do in order to help try to stop that. A couple other ones that, I didn't mention one that's in the list here, so I'm going to have to kind of double back on my notes there and jump off the beaten path, was pass the hash, all right? This is kind of an interesting technique that really revolves around things like collisions. And when we talk about collisions, we're talking about hashing collisions, right? Think about what a message digest is, right? A message digest is a one-way encryption that basically produces a fixed output, regardless of what the size of the document is, right? And we can take that output and we can save it, and we can take the document and I can hand the document over to Cherokee. And if Cherokee wants to verify that the document hasn't changed, whether malicious intent or network communication failures, she can run the same mathematical operation, right? The same hashing value across the top of that, hopefully get the same fixed length value, right? And she can compare what she knows with what she found, and if the two are the same, well, guess what? The integrity of the document's been maintained. Well, your passwords, like for instance inside of Windows, your passwords aren't really based on well, in this case, we're here in the States here, the English keyboard, right? A G isn't necessarily a G in your password. What it is that's stored is a hash value of your password. So that means that if I can find any random sequence just running my hands across the keyboard, right, that will produce the same hash value, then I don't need your password. I don't need to type in, I love my cats, right, if that happens to be your password. All I need is the hashed value, right? That's what a collision, we're trying to find the same type of hash values regardless of whether we knew what text was inside of that document. In this case, we find the same two hash values of what a password is, then I can pass the hash off to the authenticating system. I don't need the password because it's just looking down in its database for the hash value, right? It's doing the same thing that in my example of sending a document to Cherokee earlier is doing, right? It's saying, okay, you typed in your password, let's say normal operations. You typed in your password, that hash value goes to the authenticating endpoint, right? That authenticating endpoint then takes a database of a hash value it's got of your password and compares the two. If the two are the same, then you must have typed the right password. You must be who you say you are, right? Authentication by assertion. Well, now, if I have the hash value as an attacker, I just pass that off to the authenticating entity at the other end. Now, when it says, okay, I see this hash value that you just gave me, not the password, but the hash value. I see the hash value that's in my database, they're the same. I can assert you are who you say you are because when I challenged you, you gave me the right information. Again, never aware that it was the hacker on the other end, right? See, if you have a password to a user, there's no way for the endpoint to know that it wasn't actually the user that was typing it in. So the pass the hash attack can cause problems. And again, that is based on the hash value, if you will, of your password being passed off rather than what we see as the characters of the keyboard. All right, so where are we at? Well, we talked
about some wireless attacks.
Wireless, yeah, there are plenty of wireless attacks for sure. And we've got a list of them here that we definitely need to go through. One of the first ones they call out, guys, is a replay attack. That's the same thing. Any type of replay attack is where you capture information, you wait, and then you replay it later, right? This is why we have technologies that do things like time stamping and sequencing, integrity checks, right? So that time stamping alone, right? If I capture some information and it's 5 o'clock in the morning, and then I replay it to the server at noon, server looks at the timestamp, says, wait a second here, it's noon, it's not 5 a.m., and discards the packet, right? It's one of the ways we can stop a replay attack. But that's essentially all a replay attack is, whether it's on a wired network or whether it's on a wireless network.
Sorry to interject here, but just to go back, someone had put earlier in the chat, going back to that even just hybrid style of attack, if you think about, you were just mentioning the network time protocol, if you're using maybe like a Windows environment like Kerberos and it has a timeout period, and you change the times of these systems, providing a type of denial of service attack just by manipulating that network time protocol information.
Most definitely. In fact, give you a classic example where it happens a lot, and it's not malicious, right? See, in a Windows domain, your computers have to be within, by default, within 5 minutes of whatever the master time clock is. Typically, the domain controller is the master time clock. And that's why. Why does it have to be that way? Well, because Kerberos, or Kerberos, however you want to say that, is a time-sensitive ticket stamping or ticket granting authentication mechanism. And it means that when I log in, it's going to give me what's known as a ticket granting ticket that's time-stamped. Well, if my time on my computer is off by the master time clock, then those timestamps don't match. And if your computer does that, and it starts to vary more than 5 minutes by default off to the master time clock of the domain, your computer loses trust with the domain. And one of the things that you'll go in to do, you'll go in to try to log into the computer, and the computer will say, nope, sorry, this computer's lost trust with the domain, and what do we have to do? We've got to unjoin it from the domain. We join it back to the domain, it talks to the domain controller, and it synchronizes its time. Right, so time stamping is very, very important in combating things like replay attacks. IPsec is another one, but we'll get into IPsec a little bit later. Also does time stamping. All right. One of the other things that they call out is something known as an IV. Okay, in your encryption methods, specifically like we're talking about wireless, you have what's known as an initialization vector. All right, and I want you to think about this. If I have two of the same identical pieces of data, we use the exact same encryption method. Cherokee, do you think it'd be safe to say that it's going to produce the same encrypted output? Again, identical encryption method, identical data in every way.
It should.
That's right, right? It should. And in encryption, we don't want the possibility of identical frames or packets. Why? Well, because you could run code, or you could run some kind of program that does statistical analysis.
You start becoming, frequency analysis. You start becoming predictable.
That's it, prediction, exactly. We don't want predictability in encryption. So I got a little diagram here, guys, and it really isn't much, but it kind of shows you what's going on, right? With wired equivalent privacy, this is one that was very susceptible to that. It's one of the reasons you should not be using wired equivalent privacy, or WEP, on your wireless devices today. And that's because what they do is they add an initialization vector, and this is what most encryption will do. The initialization vector is always added to your data, pseudo-randomized, so that the entire thing is encrypted, and it makes sure that no two pieces of data, like we were saying, ever come out identical. We don't want you to be predictable.
Confusion and diffusion.
That's right, that's right. So here's the problem. The initialization vector, I don't know if you guys can see that, 24 bits in a WEP frame, okay? And there's a problem with that. The problem is 24 bits in anything that has to do with security isn't long enough, right? We have things like AES 256, SHA 256, 384, 512, 512 bits, okay? So I want you to think about this. If there's 24 bits in an initialization vector, that gives you 16,777,216 possibilities, okay? And the problem with that is that the statistics say that about 50% of those 16 million possibilities, just under 17 million possibilities, you're going to have a duplication, right? Because there's not a lot of bit space there. There's not a lot of chance for possibilities, even though that seems like a lot. In modern computing, it's not. And the problem is, now that you have the duplications, just like identical data identical data encryption producing the identical encrypted output, these initialization vectors become the problem, right? When we moved into things like, for instance, WPA, Wi-Fi protected access, it increased the bit length of the initialization vectors to 48. All right, 48 bits is a lot harder to crack because of combinations and how many possibilities they are. So that's the initialization vector. It's one of the reasons you should not be running wired equivalent privacy on any wireless network that you have. All right, now we get to talk about some interesting things. We talk about, for instance, evil twins, and they talk about rogue access points. I'm going to go ahead and I'm going to basically talk about them in the same context, right? Because a rogue access point, all right, a rogue access point is basically, we've got a wireless network here, right? And from time to time, we'll fire up a wireless access point to do study, to do testing, get ready for our shows, right? What happens if that wireless access point, which they do a lot of times by default, starts giving out DHCP, IP addresses through DHCP? Now here's the problem. If it's an open system like that, you can connect to it, and I don't have any internet connection. We're not going out to the internet with that access point, and now we have denial of service attack. That's a rogue access point, right? It's just any unauthorized access point in the proximity of your wireless network that people start connecting to. Now, the evil twin is still a rogue access point, but it goes a little bit farther. Now they're trying to be a little bit tricky, okay? And what they do is they take, for instance, something like your SSID, right? The service set identifier. Think of it as the network name. It's how I identify what networks are out there, right? In the little list that you have on most of your mobile devices. Well, imagine if I brought up a rogue access point and I did an identical SSID every way. So when that list, you look at that list, you say, oh, I got two, coffee spot, coffee spot. I don't really want to go in and ask the person at the desk or the coffee shop attendant, what's your Wi-Fi password, right? I can see that this one over here, this one says it's open. So it's going to make it a lot easier, right? Convenience for me, and I'll just connect to it. Unbeknownst to you, that's actually a rogue access point, and now the attacker could be just simply denial of service, or they could actually be scraping your information, right? So again, rogue access points and evil twins are almost one and the same. Rogue access point is nothing more than no configuration, right? Plug it into the wall, it starts broadcasting, and it starts handing out IP addresses. Evil twin, same thing, but now we got to go into the interface of the access point and make some changes, right? For instance, changing the SSID to match whatever the legitimate access points network is, so that it looks, or it spoofs, again, it looks just like it is the legitimate access point. All right, I know we're coming up on the end of the time, so let me go ahead and I will take care of a couple more of these here real quick. Jamming. Jamming is a denial of service attack. All right, jamming can happen. It can happen by flooding your network. Yes.
802.11 jamming.
That's right.
EMI interference there. So there's a lot of different forms of jamming also.
Most definitely. Electromagnetic interference doesn't necessarily have to be malicious, right? It's still a jamming.
Legit, yeah.
You know, so you have to be careful with that one. And we could actually do things like, you know, replay attacks could jam essentially a network where you're just constantly sending those AP station probes, right, back to the machines, the access points.
Creating a type of denial of service.
Creating the
so you guys can see how everything kind of is related in some strange, you know, family reunion kind of way here.
That's right. All roads lead back to Rome, right? That's for sure. A couple other things that they call out too. They call out, for instance, WPS, Wi-Fi protected setup. This should be disabled. In fact, when Wi-Fi protected, let's talk about what Wi-Fi protected setup is, okay? This is convenience. Is what it boils down to. It's great intentions, but you got to understand that in our little security metric here, right? Convenience on one side, security on the other. And when we go to convenience, security a lot of times drops. If we go to security, oh, did I say that right? No.
Yeah.
Okay, just make sure I say that right. That's right.
Increase security, and then we kind of have a little bit more work to do, right?
That's right, and a little bit less convenience, right? We increase the convenience, we can potentially have less security. And that's what WPS is about. WPS is about push-button security, right? Basically what I do is I go over to the access point, there's a 8-digit code, and I turn on WPS, and then in my properties of my wireless device, I put in that 8-digit code, and in the background, it's supposed to set up security for us, all right? Great intentions, good intentions, implemented very poorly. It is a risk in the way that it does authentication. It actually breaks those 8 bits down into 2 chunks. So it really is authenticating 4 characters at a time, which is really, really weak. So anyways, WPS Wi-Fi protected setup, when it first came out, if you wanted to have your Wi-Fi, the Wi-Fi Alliance type branding on it, it had to support WPS and it had to be turned on.
And it's easy for home users to use. It's almost like a yin-yang symbol with 2 arrows pointing in opposite directions. So, you know, tech support, they just say, look for that symbol, press it, you're good to go. Makes things, the convenience there is super, super nice, but not at the risk of your security.
That's right. And so what ended up happening is that they ended up doing firmware updates and pushing out a lot of the major manufacturers, because it got even worse. Like, you would disable it in the interface of the access point, but it would still be running in the background. If you're doing wireless packet capture or frame capture, if you will, you could see that WPS was still on, even though you turned it off in the settings. So a lot of them came out with firmware updates that would allow you to disable it truly if you wanted to, and that's something that I recommend, especially if you're in a Security Plus class. You're not going to be, don't take the convenience route on this one. Get in there and configure your access points to support WPA2, preferably, and preferably with CCMP. And we'll talk more about some of those concepts coming up.
Wes, I think we are out of time. We've covered a lot of different types of wireless, attacks in general, and specifically the last few we've been speaking about, we're really focused on 802.11, but we do have other types of wireless attacks to cover. I think that'll be a great place to pick right back up, so thank you for joining us, and thank you, ladies and gentlemen, but we're going to go ahead and sign out for this show. Remember, I'm your host, Cherokee Boose.
And I'm Wes Bryan.
See you next time here at IT Pro TV.
Thank you for watching IT Pro TV.